All right, hello everybody. If you guys are able to, you can just, if you're on video, just go ahead and wave that you can hear me okay. Oh, good. I see several of you on video. You don't have to be on video for this, but if you are, it makes it easier for you to like ask questions or something. I have you all muted right now because it's going to be kind of difficult to have many of you talking at once. Like, and so I just want to double check. We got 11 here, so that's good. So I don't know what Becca is doing, but it's an interesting thought, Becca. I'm assuming this is Megan that just joined us. Hi, Becca, that's better. So this, I'm sure, I know you guys have already done some classes with some of your other teachers, and so that's good. Please do not hold me to that same standard as far as my use of technology. But this is what we're at, and it's definitely going to be weird for me to teach physics in this format because you know how I like to move around and show my hands and try to describe things. But we're going to do the best we can. I will definitely take into account um, that this format may make things a little more difficult. The science department wanted us to use a different format, but it would pretty much be you learning all on your own from a computer. So I think this is going to be better. So with all that said, you guys have heard, I'm sure, that your grades you'll just get the same grade for the fourth quarter that you got for the third quarter, assuming that you complete all the assignments that I give you satisfactorily. And I'm sure that won't be a problem, but we'll hope everything goes well. On your Zoom screen there should be the option for you to be able to raise your hand if you have a question or comment or something along those lines. If you want to get hold of me, you can do that. So keep that in mind. Other than that, I'm going to go ahead and get started with our lesson today, and we'll see how it goes. Oh, also, after the lesson, I'm going to email you the actual. Hi, Carissa. I'll email you the actual worksheets that we've been doing our problems on, so that you can see that. Okay. All right. So, chapter 9, if you guys are taking notes at home, that'd be awesome. Chapter 9 is on gravity. Oh boy, this is going to be fun. Okay. Um, so, as early as Aristotle, people kind of had a sense about gravity. Aristotle obviously used his limited knowledge to describe what gravity might be, and he obviously applied that to the heavens as well, as far as the Earth and the Moon and the Sun and the other planets. There must be something that's putting them in motion, and they didn't really call it gravity, and they didn't really work to try to understand it or anything. They just said that it's the way it is. It's some higher power than we know, and we're just going to be good with that. And then along came Galileo and Copernicus, and they started to change that notion a little bit. But really, it was Newton again who really kind of changed all that. We know the story, it's not been verified, that Newton was sitting underneath a tree contemplating life. An apple fell on his head, and he said, what just made that apple fall? And while there may be some truth to that, that is not guaranteed. So what Newton decided, or what he tried to reason, is that the force that the planets would go in a straight line, as we talked about last quarter, that the planets would go in a straight line unless some other force was acting on them, pulling them towards each other, in a sense, creating orbital has. Okay. Um, he said that the force between the Earth and the apple that just fell out of this tree is the same force that pulls the moon to the Earth, so to speak. And so that was the basis or the assumptions that he made in order to try to figure out and explain what gravity between the heavenly bodies was. Okay? So he decided to test his hypothesis, and he said, well, I'm going to compare the gravity of the apple to the Earth, or the Earth to the apple with the moon, and we should be able to measure that in some way. Okay? So he reasoned that the Earth, that the moon's fall towards the Earth should be proportional or similar to the apple's fall to the Earth, right? If we just kind of use similar triangles, obviously the moon is much higher, quote unquote, higher above the Earth. Okay, and so he tried to figure that out, but it didn't work out so well. His calculations did not support the idea that the same gravity that was pulling on the apple was also pulling on the Earth. And so he took his papers and he put them in a drawer and did not touch them again for 20 years. Now, a couple of things happened in those 20 years. Towards the end of that 20 years, in 1680, not that you need to know that, a comet went roaring across the skies. And 2 years later, another comet went roaring across the skies, and it happened to be named for the astronomer that discovered it, Edmund Halley, who was a friend of Newton. Sorry about that. And he encouraged Newton to get his work on gravity back out and try again. And so he did. He made corrections in his experimental data, and he obtained excellent results. And so what came of that is he came up with his universal law of gravitation. Okay? And he said that the force between any two objects is proportional to the product of their masses divided by the square of the distance between them. We've seen this before, right? And so again, the force between two objects is proportional to the product of their masses, right? Divided by the square of their distance. Okay? Sorry, Paige. Didn't see you were up there. Let me just double check anybody else is not in. Dylan's in. All right. Sorry. Technical difficulties. Okay. So if we multiply the masses, divide it by the square of the distance, then we get this force. Now, the first thing that this should be somewhat familiar. We've already talked about this a little bit, but what happened then is he had to come up with an actual equation. And what was missing from his original equation is some kind of constant of proportionality right here. And so they just called that capital G. Okay, so capital G is the gravitational constant. Okay. Now it turns out that the gravitational constant is very small. It is 6.67 times 10 to the negative 11th power, and it's that many, let's see, Newton meters squared over kilograms squared. Okay, so that was the universal constant. Now that number is very, very small. Okay, which means that the strength of the gravitational force is very small. As a matter of fact, it is the weakest of the four known forces in nature. We have the gravitational force, we have the electromagnetic force, and then we have these two other forces which are inside the nucleus of an atom called the strong force and the weak force. But even the weak force is way stronger than this gravitational force, which is why when you are sitting next to somebody, you don't necessarily slam into each other, right? The force of gravity is not strong enough for that to happen. But why is the force, why do we stick to the earth? Well, the mass of the earth is so large that the force ends up being somewhat significant, and keeps us on the ground, so to speak. Okay. All right. So just to clarify, if we have two objects and they have a certain force between them, and then we double one of those masses, the force also doubles. If we double both masses, the force would quadruple. And then we could go into the distance things like we've done before. If we have a certain force between two objects and then we double their distance apart, the gravitational force becomes 4 times less. Okay. If we move them 3 times closer together, the gravitational force increases by a factor of 9, right? So that distance is squared. So keep that in mind. Now, again, I want to try to drive home the fact that this gravitational number right here is very, very small. Okay. It just happens to be that the Earth has a ton of atoms in it that all are applying this gravitational force on us. Now, something that's kind of cool is to talk a little bit about why, how they came up with that universal constant, the gravitational constant, because Newton couldn't figure it out. Newton knew what the gravitational constant times the times Earth was, so he knew what this product was. I'll just write this: the mass of the Earth. Okay, he knew that number, but he didn't know what each of them was independently. Okay, so he could not figure out the gravitational constant. Okay, so what finally happened is 70 years after Newton died, the guy's name was Philip von Jolly, kind of a fun name. He put a scale, right, and he put some mercury in this side. Okay, and he put a weight over here. Right? It's actually kind of a tall thing on a table. Okay, so this is like a scale, like an old-fashioned scale that you would see that would just balance, right? So he put this mercury on one side, he put this weight on the other, and then he passed a 6-ton, this is not to scale, okay, but this is a 6-ton ball of lead underneath it. Okay, once he moved that 6-ton ball of lead under there, what happened is the mercury ball right here actually started to drop a little bit. It pulled towards that 6-ton ball of lead. And so what he had to do is then he had to add weight to this side in order to make it balance again. Okay? So the amount of weight that he added, with that number, he was able to calculate what the force of gravity was, because he knew the weight of the lead ball was 6 tons. He knew the weight of the mercury. And he knew how far apart they were, right? There's a distance here. He knew that distance. And so he could calculate what the force of gravity was supposed to be. And then he could apply this universal constant, or he could figure out the universal constant. And that's where we came up with that number. Okay. So once they knew what G was, then they could calculate the mass of the Earth. Okay, so for example, if we have a 1 kilogram object, what's the weight? I should unmute you for this, but what's the weight of a 1 kilogram object? Oh, good answer. 10 newtons. Okay. So if we set a 1 kilogram weight on the surface of the Earth, we know it has a weight of 10 newtons. That's the force. Okay. So in my equation, hold on. Okay. If I now know this is 6.67 times 10 to the negative 11th, I know my force is 10 newtons, and I know the mass of the object is 1 kilogram. I don't know the mass of the Earth. Okay. Now, what about the distance? The distance is the radius of the Earth, because when we are looking at these distances squared, the distance is always from the center of mass of one object to the center of mass of the other object. So we can't just say, well, it's on the surface of the Earth, so the distance is 0. No, the distance is actually from the center of the Earth to the edge of the Earth, which we could say is the radius of the Earth, which is 6.4 times 10 to the 6th power. Now, we are squaring that, right? So without going through all those calculations, what we found out is that the mass of the Earth is roughly 6 times 10 to the 24th kilograms. Sorry, that's a 4. And so for the first time ever, 70 years after Newton passed, the world finally knew what the mass of the Earth was as 6 times 10 to the 24th power. It was such a big deal, like there was newspaper articles all over the world about it. Anyway, it was just kind of a big deal back in those days. Okay? All right. So the only other thing that I want to go through today is well, first of all, let me try something here real quick. What are we doing here? Hold on. Okay, sorry about that. I'm going to try to unmute you. If I can figure out how. That's not working. A little thing over here got stuck. Hold on. Oh, there we go. All right. All right. Okay, so if you guys have sounds going on in the background, you may want to try to minimize those, because everybody's going to get a chance to talk here. don't know why someone.
I'm digging.
I'm assuming it's because you don't have the capability, but that's all right. So, does anybody have any questions at this time? Before
Yes,
we continue?
I do.
Who's
You're
that?
on a call.
Becca. Oh
Becca.
no.
Is it?
Okay. So the distance is the radius of the Earth. LOL. The distance of the radius of the is the radius of the Earth. How?
Because the distance, we're talking about the force between two objects. We're talking about it's proportional to the product of their masses divided by distance between them squared. That distance between them has to be between their center of masses.
Okay, got it.
So the center of the mass
Thanks.
of the Earth obviously is at the center of the Earth. So, yeah. So if you want to calculate the center of the mass, I mean the force between two people, you have to measure their distance, the distance of their center of masses, not just their not the closest. All right. Anybody else have any questions?
Wait, I have another question.
Okay, Becca.
So on the little scale thingy that you drew, the 6-ton ball of lead, it was not touching the scale?
No, they rolled it like the scale was set up like it was probably more like a big, they set up this big experiment, where that kind of looks like pie. But this is like the ground right here.
Mm-hmm.
And this 6-ton ball of lead would have been massive, right?
Yeah.
And they have this little ball of mercury up here.
Oh,
Not touching.
this is the scale.
But
I was on his thing.
it would pull that ball.
Well, now I have to rewatch all of it. And it's not like
The 6-ton ball pulled the mercury?
Yes.
What? That
Does
doesn't
it-
make any sense in my mind.
Well, there's a force
okay.
between these two, right? The force of attraction between the mercury and the lead ball, because they both have a mass.
Because
Right.
he's speaking so fast, so I got 2 things of notes.
I cannot hear you if you're talking, Mr. Gurnio.
I am trying to figure out. Oh, there's my. Okay.
You just get A no matter what. Or you get the same grade the next semester.
Okay.
No matter what.
So where
So
were
Mom said.
so
So I don't have to do it.
there has to be some traction. Oh, unfortunately my internet is not great here. Wow. Perfect. So does it make sense, guys, that there has to be some force of attraction between these two balls? Becca, can you hear me?
Yeah,
Okay.
I don't know. Wait, like the 6-ton ball made the mercury roll off?
No. It didn't make it roll off. This is a scale, right? This is like I should have drawn this more like a balance like this. So it's just gonna pull this ball down towards the lead. Right? It's gonna tip. This is like a seesaw. Think of this like a seesaw, right? When you put this big old massive 6-ton ball of lead, this is probably the size of like a dump truck or something. Okay.
Okay.
So when you park this thing underneath it, it's going to pull the seesaw down a little bit.
Oh, while it's under there, not when it's
While it's underneath it. Yeah. It doesn't pull the ball off. It just kind of makes the seesaw tip a little bit down, so it's like maybe like this.
Mr. Granillo,
Yeah.
is that like how I was asking you a couple weeks ago? Like if you're in space, then like if something was close enough to you, it would just float to you because you have because like everything has a force of gravity in it, kind of.
Yeah. The two objects in space would have to be fairly
Been
massive,
selected for
but
the
yes.
advisory
Okay.
or
So do you
there we go.
understand, Becca,
At
that
least
this is tipped?
for the
Scale is
superintendent.
now going to be tipped
The
because the
schools, the
mercury is being pulled to the lead.
I'm winner today.
Oh, okay, and that's why they had to add the weight on the other side.
So yes, now we have to add weight on this side so that it balances back out. And the amount of weight that they add on this
We'll get some
side
scratchers.
tells us what the force of gravity is.
Because I got this, and I really like to
Okay.
use it.
Okay,
Okay.
guys, make sure you know you are not muted anymore. If you'd like to mute yourself, that'd be great, but I'm hearing other people talk. It's kind of annoying. So I think you guys gonna have to deal with that remotely. Come on. So, any other questions about the lead and the mercury and all that?
So as the distance gets closer, would the gravitational force lessen?
No, other way around.
Okay.
As the distance gets smaller, the gravitational force increases.
Oh, I see now.
Okay. Anybody else have a question at this point? All right. Anna, do you have a question? Anna, can you hear me? All right. Okay, so I'm going to email you guys the assignment just on that little bit right there. And then we're going to meet. So basically, I would like for everybody to plan on meeting every day at 2 o'clock, because that's kind of like our normal time would have been. And then us, we're still going to do the same thing where I'm going to give you an assignment every day. You're just going to turn it in when we're done with the chapter, and we'll just either have you, take either write your answers out electronically, or you can take a picture of your responses on paper and email that to me. However we can get that, we'll get that taken care of. Okay. All right. You're making me hungry, Becca.
Sorry.
All right. If nobody else has any questions, then we'll pick this up tomorrow. We'll talk some more about the whole distance thing and try to clear that up. All right. All right. Thanks, guys. We'll see you tomorrow.